This video is part of the MCAT Chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll go over the solubility constant, and we'll look at KSP problems, and then go over the common ion effect. The solubility constant tells you how soluble a compound is, and it's represented by this term KSP, and KSP is really just another equilibrium constant. And on the left side here, we just have K written as a general term for an equilibrium constant. And all equilibrium constants, no matter what you're dealing with, are equal to products over reactants, and then they're raised to the power of their coefficients. And also for all equilibrium constants, we exclude any pure solids or liquids. So if you look at the KSP, there is no denominator. So basically we've left out the reactants. And that's because if you look at this reaction at the top, which is just an example of a typical solubility reaction, the reactants are a pure solid. So then the pure solid gets excluded from the equilibrium constant. So KSP is basically just equal to the reactants raised to the power of their coefficients. And that's why you never see a denominator whenever you're dealing with KSP. And what KSP is telling you is the maximum amount of a substance that can dissolve. So whenever, let's say, AB is dissolving into the two ions A plus and B minus, when you multiply their concentrations, once those concentrations multiplied together reach the KSP number, no more of the compound AB will be able to dissolve. The KSP for certain compounds varies drastically, and in the last solubility video, we talked about completely soluble compounds. So completely soluble compound like NaCl here has a very high KSP. So you can kind of imagine, if you just think about this equation, how much NaCl could dissolve before the KSP is reached. Compare that to something like calcium fluoride, and your KSP is extremely small. So when you think about how much calcium fluoride could dissolve, the amount is absolutely tiny compared to the amount of NaCl that could dissolve. In the last solubility video, we talked about how you would calculate the concentration of a completely soluble compound, and right now we're going to look at how would you calculate the concentration whenever you dissolve a less soluble compound. So our problem right here is asking what would be the concentration of both calcium and fluoride if we dissolved enough calcium fluoride in a solution to make it saturated. And what saturated means is that our KSP has been reached. So not all of our compound is going to be able to dissolve because we have saturated the solution and reached the KSP. So the first thing that you do to solve a problem like this is you need to write out your reaction. And our reaction is simply calcium fluoride dissolving into the two ions calcium 2 plus fluoride minus. And always make sure your reaction is balanced. So now you also want to start considering what KSP equals. And you want to imagine that you've just put solid calcium fluoride into water and it has begun to dissolve. So we're going to write an ice table, and an ice table is really not necessary here, but I would at least go this route until you feel totally comfortable with it, and then you can stop making the whole ice table. So the I stands for your initial concentrations. So the second that we add solid calcium fluoride, nothing has dissolved yet, so our concentrations are 0 for each. And we're not going to put any amount for calcium fluoride for the solid version because that will not go into the equation for KSP. Next we have C, which represents change. So the change, we will use a variable. So we'll just do plus X for calcium. And then for the fluoride, we're going to do plus 2X because for every calcium that goes into solution, there are 2 fluoride ions. And we just get these numbers from the coefficients in the reaction. Lastly, we do E for equilibrium. And now you just do your simple addition problem. So we have X for calcium, and we have 2X for fluoride. Your final step is to plug in those numbers into the equation for KSP. So we do KSP equals the concentration of calcium times the concentration of the fluoride ions. And remember that fluoride is raised to the second power because of that coefficient. And then now we plug in our values that we calculated from the ice table. So the KSP equals X times 2X, and that 2X is raised to the second power. We know the value for KSP, so we'll plug that in for the KSP. 5.3 times 10 to the negative 9 equals X times, and then now we need to distribute that 2 to both the 2 and to the x. So it's x times 4x squared. And we ended up getting 4x cubed equals the KSP, which is 5.3 times 10 to the negative 9. So I'm going to take where we are now and finish this problem on the left side of the screen. So over on the left side, we're back where we were, and we want to approach this exactly how we would on the test, which would allow us to use some pretty generous rounding. So instead of trying to do 5.3 divided by 4, just do 5 divided by 4. So 5 divided by 4 would be 1.25. So we have x cubed equals 1.25 times 10 to the negative 9. So now you want to take the cubed root of the 1.25 by itself and then do the cubed root of 10 to the negative 9 by itself. So we end up with x equals first the cubed root of 1.25, and again be really generous with your rounding and just round that down to 1. So the cubed root of 1 is just 1. And now we have to do the cubed root of 10 to the negative 9. And if you remember how to take the square root of an exponent, when you take the square root of an exponent, you just divide it by 2. So whenever you take the cubed root, you just divide it by 3. So 1 times 10 to the negative 3. That is roughly what x is going to equal. And then remember that we said the concentration of calcium is equal to x. So then calcium's concentration would just be 1 times 10 to the negative 3 molar. And then the fluoride was equal to 2x. So we just multiply it by 2 to find the concentration of fluoride, which would be 2 times 10 to the negative 3 molar. Now we need to look at the common ion effect. And the common ion effect happens whenever we have a similar ion that comes from multiple sources. So if you look at our example down here, we have sodium fluoride and calcium fluoride both going into the same solution. So we have fluoride ions coming from 2 different compounds. And what's going to happen is that this is going to affect how much of one of these compounds can dissolve. In the practice problem we have here, we're going to show how this lowers the solubility of the compound that has the lower KSP. So in our solution, we have a 1 liter solution that has a concentration of 0.5 molar of sodium fluoride. So the sodium fluoride is already 0.5 molar. And then we are adding 1 mole of calcium fluoride. And now we have to figure out how much calcium fluoride is actually going to dissolve. Remember from the last video on solubility, we said that compounds with a group 1 metal are super soluble. That means that at these concentrations, we are not even going to be close to reaching the KSP for sodium fluoride. But for calcium fluoride, as we saw in the last problem, it has a super low KSP. So at these concentrations, we are going to be exceeding the KSP of calcium fluoride. And that means that all of the sodium fluoride will dissolve, but not all of the calcium fluoride will dissolve. So what we have to do is figure out exactly how much of the calcium fluoride is going to dissolve. The way you do this is with an ice table again. And again, practice these ice tables until you get good enough to the point that you feel like you don't need them anymore. And this changes a little bit compared to the last one because the way we want to think about this is that we have an initial amount. So in the last one, our initial amounts were 0. But in this one, because we have sodium fluoride, our initial amount of fluoride ions would be 0.5. And then calcium would be 0 still because there was no calcium from the sodium fluoride solution. Once we add the calcium fluoride, that will be the change that occurs. And for every molecule of calcium fluoride that dissolves, we will get 1 molecule of calcium ions and then 2 molecules of fluoride ions, just like before. So we need a 2x for the fluoride. And then once it reaches equilibrium, we will have X amount of calcium ions and then 0.5 plus 2x amount of fluoride ions. And now hopefully you can see where this is going. We're going to plug this into the KSP for calcium fluoride. So the KSP for that was 5.3 times 10 to the negative 9. That was from the last problem, so they'd have to give you this value. And then that equals the concentration of calcium times the concentration of fluoride. But just remember to raise the fluoride to the second power because of that coefficient. Then put in your variables that we solved using the ice table. So we have X for the calcium ions times 0.5 plus 2x, and then do not forget to square that value. Now this next part is super important because it takes something that would be extremely difficult math-wise and makes it much easier. So the 2x value that's in the part for the fluoride ions, that 2x is solely coming from calcium fluoride. The 0.5 is from the sodium fluoride. And what you'd want to think about now is how much calcium fluoride is actually dissolving. And when you look at the KSP, it's a super, super low value, so we only have a tiny amount of calcium fluoride dissolving. If we were to find that value and then add our 2x to that 0.5, we're still going to end up with a number that's extremely close to 0.5 because of how small the value for x is going to be. So what we can do is actually just cross out 2x because we're going to basically end up with 0.5 regardless. So then the right side of our equation becomes x times 0.5 squared, which is a much easier number to work with. So finally we end up with 5.3 times 10 to the negative 9 equals 0.25x. So you divide the left side by 0.25, which is basically the same thing as multiplying it by 4. So then x equals, and we're going to do some rounding here, 20 times 10 to the negative 9. So that means that our concentration of calcium ions equals 20 times 10 to the negative 9. And then remember how our fluoride ions, we already started with 0.5. And notice how tiny that value is for x. So our fluoride ion concentration is still just equal to basically 0.5. Complex ion happens whenever you have a metal cation combined with multiple anions. And in these ions, we have what's called coordinate covalent bonds. And a coordinate covalent bond happens whenever both the electrons that are in a bond between two atoms came from the same atom. So if you look at our example here, look at this top chlorine atom and notice that it has a lone pair. That lone pair is then attacking the copper ion. So the bond that forms between the chlorine and the copper, the electrons in that bond both came from the chloride ion, which makes that by definition a coordinate covalent bond. And coordinate covalent bonds are not really drawn with these arrows. The arrows are just there to show you that that lone pair is what's forming the bond between the copper and the chlorine atoms. So normally you're probably just going to see these drawn like they're normal bonds. These are really good to illustrate how the common ion effect can actually be used to make more of a compound dissolve. So if we have a solution that we have put silver chloride in, so we're trying to dissolve the silver chloride, notice that the silver chloride has a pretty low KSP, so not a lot of it is going to dissolve. So initially we've put this in solution and we think about how our ice table works, and X amount of chloride and X amount of silver have dissolved into this solution. Now if we were to add copper and we're able to form this complex ion, then that would funnel out all of those chloride ions to form this complex ion with copper. So if we added copper ions to that solution and then that reaction was able to happen, some of those chloride ions would start to funnel into that reaction, which would in turn lower the concentration of chloride in solution and then drive this reaction more to the right because the KSP would no longer be reached as those chloride ions are taken out of solution.